All right, guys. Let's start. So we stopped here at the uniform distribution. So here the uniform distribution has two parameters, which is simply the minimum and maximum possible values. Let's see. Okay. And then if that value is set as A and B, then we can easily compute the mean and the variance for it. And that was it for uniform distribution. And then the next one is a normal distribution, or also known as Gaussian distribution. Let's see. So in the case of normal distribution, as you guys are familiar with, it has the probability density function in this form. So 2 pi sigma 1 over 2 pi times square root of 2 pi times sigma, and then exp, and minus 2 sigma squared, then x minus mu squared. Right? So that's some familiar density function that we know. So here in this case, we have two parameters of mu and sigma. And in this case, these two parameters, the mu will work as a mean, and then sigma squared will be our variance, or the square root of it, or sigma will be our standard deviation. The mic seems to be kind of sensitive today, so I don't need to talk loud. So yeah, using this density function, we can compute the probability of x being in a certain range, for example, in this case. So if we want to compute the probability of x lying between x1 and x2, we can simply compute the integral of x1 through x2 of f of an x and dx, where f of an x is our density function. So it's true. It's always the true. It is always true, regardless of any distribution. So whether it's a Gaussian or any other distribution, it is always true. And so in the case of Gaussian distribution, you guys know the general shape of it. So we have a mean here, and also we have a peak at that point. So at the mean value, we will obtain the peak, the highest probability density value. So that's one property that this Gaussian distribution has. And then it's gradually decreasing as it gets further and further from the mean value. And then from this function shape, we can simply integrate these parts so that we can compute the probability. Okay. And then as a special case of this normal distribution, where we have a zero mean, or mu equals 0, and standard deviation is also same. Also set as 1. So in this specific case, instead of just calling that as normal distribution, we call that as standard normal distribution. Right? Okay, so so typically we are generally given the table that contains all the pre-computed probability distribution value for this standard normal distribution, right? So we have like a table for standard normal distribution, and then we utilize it to compute whatever value that we want, given a not necessarily standard, but the normal distribution. So, suppose we have like the normal distribution of mu equal to 2 and sigma as 2, maybe 3. Okay, so in this case, let's say the question is probability of x lying between -2 and 5, right? Okay, so in this case, it should be large X. So in order to compute this value, we first normalize this guy into another random variable z, which is a standard normal distribution. So z follows. Z follows this guy, where zero mean and the unit or the standard deviation of 1. Okay, so how we convert this guy, x, which follows the normal distribution where we have mean of 2 and standard deviation of 3. So we can compute z as this guy in this form. So it's x minus 2, or in general we can represent z in this form, right? So that way we can satisfy the zero mean and the standard deviation or the variance of 1, right? So that way, -2 to 5. So this range for the variable x changes as -2 over 3, which is -4 over 3, and then 5 minus 2 over 3, which is just 1, right? So that way we can kind of utilize the pre-computed table for standard normal distribution. Okay. Okay, then typically our standard normal distribution, I mean the pre-computed table or the pre-computed probability value, will be given in the form of this. So so the table for standard deviation, standard normal distribution will be something like this. So it will be giving you the information of this probability, where z is standard normal random variable. I mean the random variable following the standard normal distribution, but z is lying between, always starting from 0 and then various values of this right or upper bound, right? So in this case, let's say that probability was 0.15, for example, and then the table will give you the another value of this guy, right? So in the table we have 0.1, 0.2, 0.3, 0.4, and so on, and maybe 99.5, for example. Okay, so that so this is let's call that as A. So we will have the table where the input is A, and then the next column or the right column is telling you the probability of a z lying between 0 and A. Okay, so in this case 0.15, 0.2, 0.22, and so on, right? So basically the table looks like this, and then we utilize this table. So back to the previous case. So we have to compute this probability. So that's the original problem. And then in this case, we change that into so just for convenience, let's put the equal sign in both sides. Then so this probability, where we have this standard normal distribution, and so minus 4/3, and 1 is here, and so we should compute the probability corresponding to this region. Then this part is actually represented in this form, starting from 0 up to 4/3. And then for this probability, is represented as this. So we can actually utilize the two different entries corresponding to this and this, so that we can obtain the answer. So that's what we do in this standard normal distribution, and how we compute or how we convert non-standard normal distribution into the standard normal distribution in this form. Okay, there are a bunch of example that trains you for playing with the Gaussian distributions. Okay, so there are so many slides, and then let's move to this theorem 6.3, which is about the relationship between the binomial random variable and also the standard normal distribution, or in general the normal distribution. So here the main point is that if n gets larger in the binomial random variable, so you guys know. You guys remember what the binomial random variable is, right? So we have, for example, like 100 total trials, and then we actually consider the number of red balls that we picked up out of 100 total balls. So in that case, in those random variable of binomial distribution, if n gets really large, so 100 is not sufficiently enough. So it could be 1,000 or 10,000 or 1,000,000 and so on. So if n gets larger and larger, and then this distribution or the distribution for binomial or random variable will be converging to normal distribution. Okay, so that's this theorem says. And then, in the case of Gaussian distribution or normal distribution, we need a two parameter, which is mu and sigma, right? But this mu and sigma is actually computed from the binomial random variable. So, in the case of binomial random variable, we know binomial random variable was represented in this form. N and P. So we have two parameters, the total number of trials and the probability of picking up the red balls at one time. And then the random variable X is representing the number of red balls that we picked up. And then in this case, we derived the mean for this random variable is represented NP, and then variance is represented as NPQ. So this mean and the variance will stay the same. They will not change, but their probability distribution will be more and more looking like a normal distribution. Okay, so that's the main message of this theorem. Then, so between these relationships, let's consider just one more thing. Let's just note one thing. So binomial random variable is what we learned in the previous chapter, which means it's in the category of discrete random variable, right? So here in this case of an x, or the number of red balls that we picked up, it's actually integer number, which start from 0 up to n, right? So that's the possible values. Although 0 will have a certain probability of x being 0, and then 1 will have its own parameter, its own probability value, right? So that is determined as like this guy, and in the case of 1, and combination 1 times p to the power of 1 times 1 minus p to the power of n minus 1, right? So you guys know that, right? But in this case, the random variable x was discrete. It is discrete, and also it has a certain range starting from 0 to n, right? But in the case of a normal distribution, we are studying the continuous random variable, which means basically random variable value for normal distribution can have any value. So as we saw in this example, so this is one example of Gaussian distribution. And then for any possible value of an x in the continuous or the real value domain, so it will have a certain probability values for any values of an x. So basically all the possible value for x is unlimited. So it can have any value between minus infinity to infinity. And then also it is not just an integer, right? So it can have any value. So in this case, it doesn't seem to be right at first, because we are comparing, or we are saying that binomial random variable, which has this specific range as a possible values and also as an integer values, I mean that random variable, I mean the distribution for it is converging to some continuous random variable and its distribution, right? So certainly in this case, even if n gets larger and larger, so n was like, for example, like 10,000, for example, and then we will have some probability distribution, which is a discrete probability. So that's why we write the probability distribution in this form, okay? So certainly, less than 0 or negative values, or more than or greater than 10,000, the probability will be exactly 0, unlike a normal distribution where we have some probabilities for any values of an x, right? So the meaning of a convergence between these two is kind of a we are saying in a kind of approximate sense. So even though they are discrete and also integer random variable, and also normal distribution is a continuous random variable, but this kind of distribution is approximately converging, or the shape of this distribution, is looking more and more like kind of a normal, okay? And also in the case of normal, even though we have a probability in this kind of outside regions that are not where those binomial random variable cannot exist, right? But in this case, those heights or the probability corresponding to this outside region is kind of negligible. So they are close to 0, okay? So that's our kind of a rationale or justification for supporting or agreeing with this theorem. Okay, and then for this guy is not much. I mean, out of this theorem, or the meaning of this theorem is what I just described, and then this is just showing just a typical standardization process where we change the normal distribution where we have, so we have a normal distribution where the mean value as this guy, np, where n and p came from our binomial random variable, and also sigma as n times p times q, okay? So if we set those two parameters for Gaussian distribution, where which are mean and the variance, and then in this case, in order to change it to, or in order to convert it to standard normal distribution, we have to change it to have zero mean and unit variance or standard deviation. Okay, so in this case, we have to do the exact same transformation where we did in the previous slide, which is x minus mu, which is an NP in this case, and also this NP cube as our standard deviation, right? So this is just telling us just another standardization process. But here, again, the main message is this convergence, where we have larger and larger n, and then binomial distribution will look similar to normal distribution. Okay, so there is this theorem. Okay, so the next distribution. So yeah, again, so similar to last time, where we learned about the binomial or random variable, the relationships between the binomial random variable and also the Poisson random variable. So let's see. Let's try to look at the. Let's see. Yeah, so for this one, so in the last part of chapter 5, we learned about these. So binomial random variable, when n becomes large and then p becomes close to 0, where those two have the same velocity of going to infinity and 0, so that our mean value of an np stays as a constant. Okay, so if we satisfy this condition, approximately this binomial random variable will become more and more looking like Poisson distribution, right? So the reason for studying or learning about these relationships is because sometimes we cannot directly use Poisson random variable, right? But we can easily use this binomial random variable. So in that case, we can replace this Poisson random variable with the use of this binomial random variable. So that's why we use this type of theorem or relationships between different distributions. So that is exactly the same case for this relationships between a binomial random variable and also a normal random variable. So in those cases, sometimes we cannot use a binomial random variable. In that case, we have to use normal, approximate in an approximate sense. And also in the opposite case, where we cannot use normal distribution, and then we can kind of approximate it with the binomial random variable. So yeah, so that is kind of practical meaning or the use of this type of theorem. Okay, so the next one is this gamma distribution. So in order to define the gamma distribution, we first have to learn about this gamma function. Okay, so gamma function has this definition. So gamma function, so it's basically a function. So function means we have a parameter value or we have an input value, and then this function or this black box will give you some output. And this function will take a scalar parameter and then gives an output as another scalar value. So from that perspective, in order to use this gamma function, it takes an input of an alpha. Okay, so alpha is our input, and then this gamma function will give you or compute this value. Okay, so here in this case, what will be gamma 1? And also here, what you should not be confused of is this guy. So here, even though we see these x values in this representation or definition of gamma function, so we have an x in this representation, right? So they are existing inside of the integral, right? So after we compute this this kind of integral over x, and then we no longer see x value, right? So that's why we see that's why this function is not dependent at all on x value, right? Okay, so let's just try to play with this gamma function first. So what would be the value of gamma of 1? In that case, 0 to infinity, and then gamma is 1, and so it should be 1, and e to the power of an x and e dx, right? So can anyone compute quickly for this value? Yeah, 1. Yeah, it is 1, right? So when you take an exam, if you don't know the answer or you have no idea, and then the best bet will be 0 or 1, right? Okay, so in this case, we know the infinite integral form of this, which is this guy. Not infinite, indefinite, right? What is indefinite? What is indefinite integral in Korean? 네? 부정적분이죠, 부정적분. 그죠? 네, 그래서 이거의 부정적분 꼴을 먼저 하고, so once we compute this indefinite form of an integral for this function, then we actually plug this minimum value and the maximum value, right? That's how we compute this definite integral, right? Where we have a specific range of the 0 to infinity. So in this case, when we put x as an infinity, and then it's 0, and then minus and minus 1, so that's why we have 1. Okay? So this is one property. Okay, and then the other property, where we have alpha as, suppose alpha is just a one integer. So for example, alpha, so 1 is of course one integer, but what about 3, for example? So in this case, we can actually utilize some recursion. Okay, recursion. So in this case, we apply in this function. We apply some partial integral technique to this function. Okay, so that we can have a recursive formula. Okay, so in this case, 0 to infinity, and then e to the power of minus x and dx. So we do not intend to compute this one directly, but we actually utilize this. So let's just apply some partial integral. Where we have this guy, where we set this guy as dv and this u. In this case, it is d and v, 0 to infinity, minus, and then du times v and dx, and 0 to infinity, right? So that's the general, general trick that we apply. This kind of a partial integral to this kind of a integral form. Okay, so in this case, let's evaluate this guy. Okay, so x 3 minus 1 times minus e to the power of minus x, right? So it's ranging from 0 to infinity, minus 0 to infinity. So this is 3 minus 1 will be coming out, then x to the power of 2 minus 1, right? Because we subtract 1. We subtract this by 1, then minus e to the power of minus x and dx, which is v, right? Okay, so that's kind of boring, right? Up to this point. So let's evaluate this part. So in the case of this value, so let's plug this infinity to the place of an x. So it's like infinity to the power of 3 minus 1 times minus e to the power of minus infinity. So what would be the value for it? What would be the value of this guy? Would it be infinity or 0 or some other value? So here the tricky part is this part is going to infinity, and then this part is going to 0, right? So who beats who? So overall it will converge, I mean the entire part will converge to 0. Because in terms of a velocity, you guys know exponential functions are much faster than any polynomial functions, right? So that way, this guy is definitely beating this guy. So in this battle of infinity and 0, 0 wins. So this becomes 0, and then okay, so let's evaluate when x is 0. So it's a 0 to the power of minus 3 minus 1 and e to the power of 0. So it's definitely 0 because even though this guy is 1, this part is exactly becoming 0, right? So both of them are 0 when plugging x with this infinity or 0. So this part is basically negligible. It gets gone. So we are ending up with this part. Okay, so we have a minus and minus. So we change it to a plus sign. Then let's take this part out. And then this one will become minus 0 to infinity, x minus 2 to the 2 minus 1, and then e to the power of x dx. Okay, so although it was a little bit tedious, but now let's compare this form with this form. Okay, so this one was originally the function value when alpha was 3. Okay, so alpha only plays at this place, right? So alpha is only appearing in this position, and now it will have the same form where we have an alpha as 2. So that way it's like this. So this guy is 3 minus 1 times 2. Okay, so again we have this kind of relationship. Okay, so in general, if we have an integer of an n, then it will be this form. Okay, so we have this type of a recursive formula. So if we want to compute this value, we know the starting value as 1. So we computed this one in this part, right? So in order to compute alpha, the gamma of 3, so we first compute gamma of 2, which is 1 times 1. Gamma 3 will be 2 times gamma 2, which is 2 times 1 times 1, which is 2. Or in general, it is something like this, 2 factorial. So in the case of gamma of n, then it will be formulated in this, it will be computed as this, n minus 1 factorial, right? Yeah, so that is kind of a general form. I mean, the several properties that we have for this gamma function. Okay, so let's see, let's look at the book a little bit for this gamma function. So just we saw earlier, so we have this type of formula. So that's one property that this gamma function has. And so for integer, we have this factorial form. And then we computed the gamma of 1. And then also additionally, we can also compute when alpha was 1/2, and then if we compute the gamma function, then it will be square root of pi. Okay, so we learned this type of gamma function. Okay, so this is just a function. Okay, so it's nothing to do with any kind of distribution up to this point. But now this gamma function is actually used to define some probability called gamma distribution. Okay, so in order to, so it's just another continuous random variable and its distribution. Okay, and that distribution is defined in this form. So first of all, it lies in the continuous or real value domain, but if x becomes negative or 0, then we assign completely 0 probability, right? And then in the case of positive x value, the probability density function is defined in this type of complex form. Okay, so it looks quite complex. I don't even remember what this form is. Okay, but here we have to know, so this, in order to call this as valid distribution function, we have to satisfy several properties. So one of such property is, so this value should be always greater than or equal to 0, right? So we cannot think about the negative probability or probability density. And at the same time, one interesting thing or one non-trivial thing is that we have to satisfy this, this equation, so that the total integral over the entire range of an x for this probability density function is always should be computed as 1. Okay. So in that case, so let's verify that. So minus infinity, infinity, and then we plug, or we bring this scary looking density function, alpha minus 1 e to the power of x minus beta times dx. So we have to verify this one, integral of this guy is 1. Okay? And then here in this case, so this looks really complicated, but let's just filter some part out. So in this case, so it's basically an integral over x, right? So when computing the integral, it's only dependent on x. So in this case, this is just a nothing but constant. So it's a fixed value over all the different x values, right? So that way we can factor it out, or we can move this guy out of this integral part. And then the integral becomes this guy, right? And then also, one thing that I missed here is that we assign 0 value for this probability, this function. So this integral should start with 0 to infinity, right? So here in this case, if this integral is computed as this value, and then we can easily, properly verify this value is becoming 1. Okay. Okay, so here in this case, gamma of an alpha is defined in this form. Okay. Okay, so this guy, this integral is the definition of gamma function when alpha is an input parameter, and this part is actually part of our denominator in this part, right? And then let's compare the expression within this integral part and also the actual integral that we have to perform in this case. Okay, so here in this case, the only difference is where? Where is the difference? Okay, I have to use different color. So this part, right? So x to the power of alpha minus 1, and then instead of just an x, we have now have x over beta. Okay, so we can change this integral, okay, this integral into this kind of form. And how? So here in this case, so we can change x prime as x over beta, right? And then this one will become x prime, and now this part will be beta times x prime, right? So we are plugging this guy into this part, right? And then beta to the power of alpha minus 1 will factored out of the integral side. I mean, we are trying to match this expression with the definition of this gamma function, right? So in addition to this gamma function, okay, we have this additional kind of a constant through this type of a conversion, okay, which is beta to the power of alpha, okay, that will come out of the integral. So basically this part will be the same as this denominator, which will give us just the value of 1, okay. So that way we can kind of verify the integral of this function over all the entire range will become 1. Okay. So that is how we utilize this gamma function with into gamma distribution, or random variable with the gamma distribution. Okay. And then this kind of figure is a different function shapes when we change alpha and beta. So here in this case, we can view the parameter to specify this gamma distribution as alpha and beta. Okay, so it's something like this. So let's call that as g, and g of an x. And what is our parameter? We have to specify alpha and beta values. Okay, in order to fully specify this function. Okay. So depending on the different alpha and beta values, these different shapes of a function will be one particular probability distribution function. But at the same time, in this case, each function will be the integral of each function will always become 1. So in this case, this part will become 1, or this part for the second function will become 1 as an integral part. Okay. And also, let me add one last thing. So as a special case where we have two parameters, alpha and beta, and then if we set alpha as 1, okay, in that case we specifically call that distribution, or that special case of gamma distribution, as exponential distribution. Okay. Okay, so time's up for today. And yep. Any questions before ending the class? 시험 범위는 그때도 얘기했듯이 이제 5장 다 들어가고 지금 6장을 배우고 있고요. 6장에 아마 전체가 되지 않을까 싶어요. 7장은 전혀 안 들어갈 거고. 네. 너무 조금이에요. 그 다음에 나도 시험이 어떻게 될지 잘 모르겠거든요. 근데 최대한 나도 좀 일찍 좀 준비를 하고 그 다음에 어떻게 공부해야 될지에 대한 약간의 좀 가이드라인을 조금은 줄 수 있도록 할게요. 근데 기본적으로는 이런 적분이나 뭐 이런 거, 뭐 이렇게 하는 거, 무한급수 이런 거 좀 잘 자유자재로 좀 할 수 있어야 되고, 뭐 숙제에서도 봤듯이 여러 연습 문제, 이그잼플들에 대해서 여기에는 뭘 적용해야 되겠구나 이런 것들에 대해서는 조금 뭐 그런 게 좀 퍼밀리어하게 좀 돼야지 될 것 같아요. 증명이요? 내부는 10분인데 어떨지 잘 모르겠어요. 네. 숙제를 그래서 네, 오늘 중으로 숙제를 내주도록 할게요. 그래서 다음 주 수요일. So the homework will be out today to cover the chapter 5 and chapter 6. Okay. And then the scope, exam scope will be probably the full, up to the entire chapter 6. I mean, up to the end of chapter 6. Okay, that's it for today. Thanks. x가 들어가거든요. 베타 x가 들어가서 이 자리에 이제 치환 적분을 하면 베타 x 프라임이 들어가요. 그죠? 그러면 x 프라임 그대로 이제 알파 마이너스 1승으로 내두고 이 베타의 알파 마이너스 1 이게 예를 들면 이렇게 밖으로 빠져 나올 수가 있게 돼요. 네. 그러면 그게 뭐랑 똑같아지냐 하면 이 안에 거가 그러면 뭐랑 똑같아지냐면 정확하게 감마의 이 알파가 돼버린 거예요. 네, 그런 식으로 우리가 증명을 할 수가 있어요.
그리고 이거가 왜 중요한 거예요?
네?
이 펑션이 왜 중요한 거예요?
이게 나도 왜 중요한지 나도 많이 안 써서 잘 모르겠는데 여기저기에 많이 쓰이는 그런 유용한 어떤 그 분야들이 굉장히 많이 있는 것 같아요. 네. 그래서 배우는 거고.
우리가 저번에 냈던 과제 다음 주에 보여주나요?
다음 주에 올려주도록 할게요. 네, 1부터 6. 네.